Hello students, Mr. Courtney here. In this video we're going to be looking over molecular geometry as it pertains to the VSEPR model, and we're going to find out what VSEPR means. Okay, so VSEPR or VSEPR model is the valence shell electron pair repulsion model, or sometimes called the valence shell electron pair repulsion theory. Why do we use VSEPR? We use VSEPR to predict the geometries or the shapes of molecules formed from nonmetals, or basically we say predict the geometries of covalent molecules. We look at the geometries of the bonding and non-bonding pairs of electrons around the central atom. So that means we have our central atom X. Let's say we have a lone pair here, and we have bonds attached to it. So we look at the geometry of the bonds, the electrons that are shared in the bonds. That will give us our molecular geometry. And then we look at the electrons shared along with our lone pairs. That gives us our electron geometry. Now, why do we call it valence shell? Remember, we draw Lewis dot structures, and from the Lewis dot structures, we use our valence electrons. So the electrons in the valence shell. Now remember, electrons are all negatively charged. So when you put two negative charges close to each other, they tend to repel. So that's why we call it the repulsion model. So how do we determine the shape? We look at the number of regions of electron density around the central atom. So we have our central atom. Now we have different atoms around it. Now, when we look at the bonded electrons, we count single bonds. So if we look at this, it has two groups attached to it. 1, 2, and this is our central atom. So a single bond, whether we have a double bond, it still counts as 1. This counts as one group, one group. So we have two groups around our central atom. Now, even if we have a triple bond, we still count this as one group around our central atom. So this is one group, two groups. So we still have our two groups around it. Now, if we add lone pairs, a lone pair of electrons around it, then we're saying still, now we have two bonded groups, two bonded groups, and one lone pair of electrons. So in other words, we have three groups or three areas or three regions of electron density around our central atom. And we'll do some examples as we go along so you can understand that better. Molecular geometry, and I kind of hinted to that already, is the three-dimensional arrangement of the atoms that make up a molecule. So how are these atoms arranged around the central atom? So we have our central atom, whatever it is, and we have Y. How will these two be arranged around our central atom X? What if we had another Y? How will that be arranged? Let's suppose we had Z. How will that be arranged around our central atom? Now, when we get to our electronic geometry, it's the same three-dimensional arrangement, but we look at the bonding pairs. So these here represents our bonding pairs and our lone pairs. So we look at the geometry of our bonded pairs and lone pairs around the central atom. So you have this table where we're going to look at the electronic structure. Then we're going to look at the molecular geometry or electronic structure and molecular structure. Then we're going to look at examples of Lewis dot structures. So to get this, note when we look at the areas of bonds and the areas of lone pairs, when we add those, we always get the total number of areas of electron density. So that's what we're going to be looking at. So on the examples we're going to look at some structures, see which section, electronic structure family, or in the geometry they fall into. We can also look at bond angles. And the last thing we're going to look at is their polarity, molecular polarity. And this is just the second part of the table. So let's start with the examples here now. Okay, you had to draw these for homework. Now you can also follow along, and I'm going to go in order from the top of the chart to the bottom of the chart. That makes it easier for you to follow along. So let's look at BeH2, beryllium hydride. When we draw the Lewis dot structure, now we see we have two. This is beryllium as our central atom. We have two groups attached to it. So when we look at our areas of bonds, we have two areas of bonds. We have no lone pairs. When you look at it, if you look at a chart, two areas of bonds, no lone pairs. We have two areas, total of electron density. That makes it linear, right, in a straight line. We look at our bond angle from here to here, it's going to be 180 degrees. Now let's look at our second one, the carbonate anion, CO3. Now all this is showing us here, remember we talked about resonance structures, different ways of drawing the same compound, or the same molecule, sorry, that would work better. All we're doing here is that we're changing the position of the double bond. That's all we're doing. So they're resonance structures. Now if you look at the shape it will take, we have 1, 2, 3 groups. Either way you look, we have 3 groups around the central atom carbon. So 3 bonded groups. We have no lone pairs around it. So 3 groups, 3 areas of bonds, 0 lone pairs. That gives us trigonal planar as our electronic structure. And also trigonal planar as our molecular structure. 3 bonds or 3 groups in a plane. And our bond angles will be 120. Now, why do we have a bond angle of 120? Remember we said the electrons want to be as far apart as possible. So that's the best way for these 3 pairs of bonded electrons to be spaced apart. So they're at 120 degrees. NO2. Again, we have a resonance structure for NO2. Now we look at our bonding groups. Nitrogen is our central atom. That's 1, 2 bonding groups. Now we have a lone pair on the central atom. So we have that lone pair on the central atom. So the lone pair is going to push the bonding groups as far apart as possible because the lone pairs are going to occupy a lot more space. So when we look at that now, 2 bonding groups, 1 lone pair, we have a total of 3 areas of electron density. So it's going to be trigonal planar for our electronic structure, but our molecular structure now is going to be bent. Why do we say bent? Here, bonding group, and here we're going to have our lone pair occupying the space at the top here, and it's going to repel these bonding groups and push them far apart from it as possible. And that's why we end up with an angle that is going to be less than 120 degrees. So that angle for trigonal planar bent will be less than 120 degrees. Methane, CH4. So this here is our electronic structure, carbon in the middle as usual. 1, 2, 3, 4 groups, 4 areas of bonds, 0 lone pairs. So we get tetrahedral as our electronic structure and tetrahedral as our molecular structure. So let's see why we get tetrahedral. Again, the bonding groups want to be as far apart as possible and in 3-dimensional shape. All right, you'd expect them as 4 groups, 360 divided by 4, you expect it to be 90. But because it's in 3 dimensions, our bond angles will be 109.5. And if you look at the shape we get here, so we form a tetrahedral molecular structure and a tetrahedral electronic structure. Ammonia, NH3. So if we look at our bonding groups and lone pairs, we have 1, 2, 3 bonding groups and 1 lone pair. If you look on your chart, 3 bonding groups, 1 lone pair. That gives us 4 areas of electron density. So it's going to be tetrahedral for our electronic structure, but our molecular structure will be trigonal pyramidal. Now how does trigonal pyramidal look? Now I'll connect these here. So we have a triangular base pyramid. That's what we're looking at. Trigonal pyramidal. So we have a pyramid with a triangular base. That's our molecular structure. Trigonal pyramidal. If we look at it here, just like this, trigonal pyramidal. And here I forgot to say the bond angle. The bond angle would be less than 109.5 because we have that lone pair at the top. And it's actually somewhere around 107 degrees. Water. H2O. So how many bonding groups do we have around oxygen? 2 bonding groups along with 2 lone pairs. So we're going to have 2 areas of lone pairs, 2 areas of bonding groups. So we have a total of 4 areas of electron density. Remember, the lone pairs, they're going to occupy most space because they're going to push, and they're going to push the bonded groups further apart. So if we look at it, we look at our just electronic structure, or electronic geometry. Our electronic geometry will be this: 1, 2, 3, 4. We have 4 groups in total, so that makes the electronic structure tetrahedral. Now we have our bonding pairs here, and we have our lone pairs. So that is going to give us a bent shape. Okay, and if it's bent, we're going to expect the angle to be somewhere around 109.5. Is actually going to be less than 109.5 because you have 2 lone pairs now. So that angle is actually somewhere around 104.5. Okay, now we're on to PCl5, phosphorus pentachloride. So we have how many? We have our central atom phosphorus. We have 1, 2, 3, 4, 5 bonding groups. And if you look at its 3-dimensional shape now, or 5 bonding groups, 1, 2, 3, 4, 5. That's going to contribute to our electronic structure also and our molecular structure. So when we look at it, we have a pyramid. So you have one pyramid here. That's one pyramid here. Now you also have another pyramid at the bottom, and the base of the pyramid is trigonal because you have a triangle, or it's triangular in shape, and you have 2 pyramids with the same base, so it's trigonal bipyramidal. Okay, so it's trigonal bipyramidal. Now we're going to have 2 different bond angles. We're going to have our axial along the axes, so between these 2, so they go top to bottom, the bond angle between these. Or we're going to have our equatorial, those along the equator, so the bond angle between these here. Our axial bond angle will be 90 degrees. And our equatorial bond angle will be 120 degrees. SF4. So we look at this, count our bond, central atom, sulfur, bonding groups, 1, 2, 3, 4. 1 lone pair. So what does that give us? We have 4 bonding groups, 1 lone pair. That gives us trigonal bipyramidal because we're still going to have that same shape. So if we look here, we're still going to have that shape, that same shape we had before. Same pyramid at the bottom. So it's trigonal bipyramidal for our electronic structure. Now our molecular structure now is seesaw. So think of this, we take this and we rotate it in this direction, and this goes in this direction. And you put it flat like this. So this is this. Our bonding groups here, here, and here. And our lone pair at the top. That's where our lone pair will be. Now think of it like a seesaw. You apply pressure here, this side goes down. This side goes up. Or you do the opposite. If I apply pressure here, then this side will go up. Just like a seesaw would operate. That's why it's called. The molecular structure is seesaw. So our axial bond angle would be less than 90 degrees. And that's because we have the lone pair of electrons. So these will be pushed closer together. And our equatorial bond angle will also be less than 120 because we have that lone pair. So they will also be pushed closer together. further apart from the lone pair. Bromine trifluoride, BRF3. Let's look at our bonding groups around bromine. 1, 2, 3, our areas of bond. We have 2 lone pairs. So we still have a total of 5 areas of electron density. So that gives us the electronic shape of trigonal bipyramidal. Remember, 1, 2, 3, 4, 5. So that's trigonal bipyramidal for our electronic structure. Now when we get to our molecular structure, look at the arrangement of our bonded groups, or areas of bonds. 1, 2, 3. It looks like a T, so it's called T-shaped. And I'll do it, just flip it around so you can see it better. This is our central atom. One bonded group, bonded areas of bond, another area of bond, another area of bond. Looks like a T, so that's why we call it T-shaped. And our bond angle for T-shaped will be less than 90, and that will only be axial, because now we don't have any equatorial. We have 2 of our lone pairs are on the 2 lone pairs are on the equatorial, so there's no equatorial bond angle. We only have axial bond angle. All right, so let's look at this one here now. Iodine is our central atom. 2 chloride ions around it, so 2 chlorine atoms around it. So that's 2 areas of bonds, and we have 1, 2, 3 areas of lone pairs. So that's 1 area here, 1 area, 1 area. So notice now, we have a total of 5 areas of electron density. So again, the electronic structure will be trigonal bipyramidal. But now, we only have axial areas of bonds. And because we only have axial areas of bonds, our molecular structure will be linear. And if it's linear, do we have any equatorial bond angles? No. And our bond angle will be, guess what? If it's linear, straight line, it's 180 degrees. All right, SF6. So let's look at that one. Now, sulfur, central atom, 1, 2, 3, 4, 5, 6 fluorine atoms are on it. So we have 8 areas of bonds, 0 lone pairs. So our shape is octahedral. And you may be thinking, how do we get octahedral from this with only 6 groups around it? Here's how we get it. Now, this may not be the best rendition of it, but I'll try my best to get it so you can see. So if we count this as 1 face, okay? There will be another face here, so that's 2. There'll be 1 at the back, fill in here. There'll be another one between these 3 here. So that's 4. That's 4 faces. 4 faces at the top, 4 at the bottom. 8 faces in total, so it's like an octahedron. So it's octahedral. Since we only have areas of bonds, then our molecular geometry will also be octahedral. And our bond angle will be 90 degrees. BRF5. So let's look at this. Bromine, 5 fluoride atoms around it. So that's 5 areas of bonds. 1 area of lone pair, so a total of 6. Once the total is 6, we know the electronic structure will be octahedral. But what is our molecular structure? Since we only have 1 central atom and 1, 2, 3, 4, 5. So we form a square base pyramid. A pyramid with 4 sides on its bases. So we call it square pyramidal. Our bond angles will be less than 90 because of the presence of our lone pair of electrons. So our bond angle will be less than 90 degrees. ICl4 minus. Central atom, 1, 2, 3, 4 bonding groups, or 4 areas of bonds. 2 areas of lone pairs, so that's a total of 6 areas of electron density. So that's octahedral. for our electronic structure. Now our molecular structure, we just have 4 groups in the same plane. So that's a square planar, because we have a lone pairs here, lone pairs here. So that's square planar. Again, repulsion. So you always have to think, once there are lone pairs present, we're going to push those bonds as far apart as possible. But since the lone pairs are in this direction, it does not affect the 4 bonding groups in the same plane. So our bond angle will be 90 degrees. So, polar versus non-polar. It says, help, help, I'm dissolving. And he says, but bears are insoluble. That's easy for you to say, you're not polar. I mean, it sounds corny, it is corny, but if you remember what we said about substances in class before, we talked about polar versus non-polar in terms of bond polarity. When we looked at bond polarity, so we talked about bond polarity, we determined bond polarity based on electronegativity difference. Remember that? So based on the electronegativity difference between the atoms in the compound, we determined the bond polarity. And we stated that like will dissolve like. So if something is polar, it will dissolve in a polar substance like water. If it's non-polar, it will not dissolve in a polar substance. It will dissolve in something that is non-polar. So here, a polar bear falls in water. Right? So the polar bear is polar. It will dissolve. Well, theoretically, it will dissolve in water. So that's what this is trying to show you here. Now, when we look at the polar versus non-polar molecule, it's a bit different. We have certain guidelines to follow to determine that. Now, if we have our central atom, let's use X as our central atom. So I have my bonded groups. I have 2 bonding groups. I have no lone pairs on it. Okay? If I have no lone pairs on the central atom, it's going to be non-polar. Also, I need to have the same type of atoms attached to the central atom. So we have X, 2 Y's attached to it, 2 bonded groups of Y, so they're the same. No lone pairs, so this is going to be non-polar. But I have the same X. Let's say I have X as our central atom. I have Y. Let's just call it Y and Y. But now I have a lone pair on it. I have lone pairs, so that will make this polar now. Also, I could have this. I don't have any lone pairs on it, but I have different atoms attached to the central atom, so that will make it polar. And that's how we're going to determine. So what we're going to do now is go back and look at the examples we had and determine their polarity. You can actually pause the video, go back and determine them, and then I'll go back with you and we'll do it together again, and you can check your answers, okay? And actually, here's what you're going to do instead. You're going to determine those, look at them, and when we come to class next time, we'll look at these first thing to determine their polarity, okay? Alright, let's look at 2 exceptions when we look at the polar versus non-polar. First one we're going to look at is ICl2. Alright, and you can go back to the structure that we had for that. We had our iodine. Okay. Chlorine around it. Now we had how many bonding groups around it? Okay. And you said 3, so we had our 3. Sorry, not bonding groups, but lone pairs. We had 3 lone pairs around it. Now, when we look at this structure, I'm not doing the whole Lewis dot structure. I'm just looking at the lone pairs around it. When we look at the lone pairs here, the way the lone pairs are arranged, they're going to be arranged in the most symmetrical form. And because of that symmetry arrangement, the 3 lone pairs are going to be symmetrical. So no part of the atom is more positive or negative than the other. So this is going to be non-polar. The other exception is ICl4 minus. Okay, so when we look at it, however we want to put it. We have our two lone pairs. Again, think of symmetry. The lone pairs are symmetrical, so there are no side of the atom will be more positive or negative, so that makes it non-polar. So we have to look at polar versus non-polar, and we look at the symmetry of the lone pairs around the central atom, and these are the exceptions that we're going to come across when we look at these. Okay. All right. So until the next time, blessings. I'm out. Oh, I also have models for those of you who missed class. I'll have models laid out at the back of the classroom so you can come in and look at these models to help you visualize these shapes also. All right, so yeah, this time blessings. I'm out.